So now we're getting into Calc section 3.4. So this is about like concavity, which is about the second derivative. So really everything we're going to do is very similar to what we've done with the first derivative. We're just going to do it with the second derivative. But now, instead of finding if it's going to be increasing or decreasing, so increasing or decreasing, we're going to be finding if it's concave up or concave down. And so, I mean, just think about what that means in English. Concave, that means it's looking more like this. And so if it's concave up, it's looking like that, like a positive parabola. If it's concave down, it's looking like a negative parabola. So, yeah, that's what we're going to be looking for here. And we're going to do it in similar ways to how we did increasing and decreasing. So the way that we look to see where it was increasing or decreasing, we look to see where the slope was 0, because that's where it switched from increasing to decreasing. We're going to do the exact same thing for concavity. So we're going to find the second derivative and see where it equals 0. Because when it's concave up, that's going to be when the second derivative is positive. When it's concave down, that's when the second derivative is negative. So we've got to look for where it switches from positive to negative. Probably where it's undefined too, to be honest. Let's look for those as well. So let's do that. Let's take the second derivative. So first we got to take the derivative. So let's see. I'm going to think about this with quotient rule. So with quotient rule, the derivative of 6 is 0, so that all goes away. So we have then minus 6 x squared plus 3 divided by x squared plus 3 squared. So that's canceling. That's canceling. That's not even right, though. That's x plus 3 squared on the bottom. This is the derivative of x plus 3 squared. This is just 2x. So that's our first derivative. Negative 12x over x squared plus 3 squared. Right? Yes. So now let's find the second derivative. So the second derivative, now we really got to use quotient rule. So it's going to be negative 12 x squared plus 3 squared minus, but then plus 12x, but then times the derivative of the bottom, which is now 2x squared plus 3 times 2x. Oh, that's kind of brutal. All over x squared plus 3 squared, except for not squared because it's squared squared, so to the fourth. So then what do they want us to do? They want us to multiply all that out, sort of. Or what do they want, though? They want when this is undefined. When is this going to be undefined? When the denominator is equal to 0. When is the denominator going to be equal to 0? Never. Because it's x squared, which is always positive, plus 3. So all we need is when the top is equal to 0. So let's just go for when the top is equal to 0. So just for the algebra, I'm going to factor out an x squared plus 3 on the top. So that's going to leave me with negative 12x squared plus 3. And then plus 48x. Right? Check my math if you would. And then I'd factor out a negative 12. So I have negative 12x squared plus 3 times x squared plus 3 minus 4x. I'm not even trying to do it. I'm trying to set this equal to 0. So now I see that it's going to come from this. And so what I'm going to get is x equals 1 and 3. So that's where the concavity is 0. So what we're going to do is set up the number line just like we did last time to see where the concavity is what. So here's x equals 1, here's x equals 3. So we're going to plug in a number in between them. And we got to plug it into the second derivative, right? Because we got to see if the concavity is positive or negative. Well, that's kind of tough. Well, let's look. So the bottom we said was always positive. So we've really just got to look at the top. And this is the top right here. So when we plug in a 2, we've got negative, then positive, and then negative. You get negative 1. So it's negative times positive times negative. So this is positive here. That's concaving up. So there the graph looks roughly like that. And so now I'd imagine it's concaving down on the outsides. But let's see. So when we plug in x equals 0, we have a negative times a positive times a positive. So that's negative when you plug in 0. On 3, you get, well, not, you can't plug in 3, you got to plug in 4. If you plug in 4, you get a negative times a positive times a positive. So that's negative again. So that's roughly what this graph is looking like. So what did they ask us for? Concave up. Up is from, and let's see, we should do it open because, like we said, it's not concaving up at 1. It's concaving at 0 at 1. That's actually what we're going to call our points of inflection, where it switches concavity. That's really what we just found, is that our possible points of inflection points, just like when we found the critical values, and those were possible mins and maxes, where it's switching from increasing to decreasing. What we found here, when we found the 1 and the 3, is the possible points of inflection, where it switches from concaving down to concaving up. And so that's what it should be. I would like to take a gander at that graph and just make sure that I agree with what we said. So this graph, 6 over x squared plus 3. So no vertical asymptotes. That makes sense. Okay, so all of that is wrong, right? Maybe not. Wait. It's definitely not switching from 1 to 3. How did I mess this up so hard? Oh my goodness. Did I make an algebra mistake somewhere? That's x minus 1, x minus 3. Did I make a derivative mistake? And see, that's why calc can get tough, because there's just so many layers, so many different places to make mistakes. So what is this? I tried to use quotient rule. So I had the derivative of 6, which was 0 times whatever, but then minus 6 times the derivative of the bottom divided by the bottom squared. So that got me negative 12x over x squared plus 3 squared. And then I did quotient rule again. So I had the derivative of the top, which was negative 12 times x squared plus 3 squared, plus, or then minus, but then times negative 12x, so plus 12x times the derivative of the bottom, which was 2 times x squared plus 3, but then times the derivative of the inside, which is 2x. So that's how I got, well, then I factored out the x squared plus 3, so I got negative 12x squared plus 3 plus 48. Because the 12 is all still in there. I just pulled out that x squared plus 3. So that's 4. That's 2 times 2, which is 4, times 12, which is 48. And then I factored out the 12 from everything. So that's how I got the x squared plus 3 minus 4x. But that definitely only gets me... Oh, wait. No, that definitely only gets me 1 and 3. That is strange. I was feeling so good about that too. It's just got me thinking that I typed the graph in wrong. Hang on, let's see what happened. I figured it out. I missed an x. Look, you got an x there and an x there, but then I only made that x. That should be, let's change colors. That should be x squared. So what does that change? So that means this should be x squared. So that means this equation here should not be that. It should be negative 3x squared plus 3 equals 0, which then you subtract 3, divide by 3, you get x squared equals 1. And so you get x equals plus or minus 1. That's what it is now. So let's see what we can salvage. Well, we plugged in 0, and it was concaving down when we plugged in 0. So let's just add these on the graph. So it should just be a negative 1 here. And everything we've found is not necessarily Well, no, I guess it is wrong because it's a different equation we're using now. So I guess we do have to replug in everything. So now our correct numbers are -1 and 1. And so we say the bottom is still always positive. When we plug in 0 to the top, I'll look at what equation should I look at? This -3. Well, I could factor the -3 out to the outside, actually, and make that positive, and just make this x squared minus 1. Yeah, so the whole thing is when I plug in 0, everything is positive, but that x squared minus 1 is negative. So this is negative. But then when it's bigger than 1, everything is still positive. But when you plug in like a 2, that's 2 squared minus 1, that's positive. And same with the -2. So that's what it really should be. And our graph reflects that as well. So let's see, it's concaving up from -infinity to -1, and from 1 to infinity, and it's concaving down from -1 to 1. It's unfortunate little math error there. What was the math error? I just didn't see all the x's. That is a tad unfortunate. But that's why I'm glad we graphed it, so we could check our answer. So here's the next problem. Determine the open intervals on which the graph is concaving up or concaving down. Actually, the exact same problem that we just had. So I think maybe with a lot of these, the hardest part is going to be finding the derivatives. Because here we got to use quotient rule right away. So we've got the derivative of the top times the bottom minus the original top times the derivative of the bottom. All of that divided by the bottom squared. Okay. Should I try to simplify this at all? Definitely. There's the 2x times x squared and the 2x times x squared. Those are going to cancel each other out. So we've just got -8x minus 2x. So -10x over x squared minus 4 squared. That's our first derivative. And then so we got to find the second derivative. So the second derivative is -10, derivative of the top, times the original bottom. I'll try to not mess this up this time. And then, again, just like last time, it'll be plus, because it's minus -10x times the derivative of the bottom, which is 2x squared minus 4 times 2x. Divided by all of that squared. But let's see, now there's asymptotes that we need to be worried about. So we do need to be concerned about when is this undefined. This is going to be undefined at x equals plus or minus 2, right? Because that's when we're going to be dividing by 0. So those we're going to have to look at. And then we got to say when is the top equal to 0. So I'm going to try to do the same exact thing as last time. I'm going to factor out an x minus 4. So then I've got -10 x squared minus 4 plus 40x squared. Right, and I want to say when does that equal 0? So I get the plus or minus 2 again. But then I'm going to distribute this, -10x squared plus 40 plus 40x squared. And I got to say when is that equal to 0? So I'm getting 30x squared plus 40 equals 0. So x squared is -4/3 and square root both sides, and I get an I. Well, that's not actually going to be a 0. So maybe it's only a plus or minus 2 then that it's going to go out. Because see, this is only going to be 0 at imaginary numbers. And that makes sense because it's a squared thing added to something else. So this is going to be no solution. We actually only have to look at 2 and -2. So -2, 2. And then we're going to plug in values. And again, we're going to plug in values to the second derivative. And just like before, the bottom is always positive because it's to the 4th power. So we're really just looking at here. So when I plug in 0, I get -4 times, I'm going to actually write this down, -4 times 40, which is negative. So it's concaving down there. At somewhere like 3, this first part is positive, because it's like 9 minus 4. And then I'm actually going to do the math out. So you plug in 3 to the next part. 3 squared is 9, minus 4 is 5. So that's a positive number times negative 50, plus like a massive number, plus like 360. So this is going to be concaving up. And then I imagine it's going to be the same thing when you plug in negative 3. And look, it absolutely is, because everywhere there's an x, it's squared. So this is an even function, symmetrical over the y-axis. And if you plug in negative 3, the exact same thing will happen as when you plug in positive 3. So that's what this should be. Now let's check. So it's got those asymptotes. I mean, really, it's just going to look like, what is it? This. It's just going to look something like that, because you got your 2 vertical asymptotes, and you got your horizontal asymptote at 1, because it's an x squared over x squared. So x squared plus 1, close over x squared minus 4. Yep, exactly what I said. Concaving down in between negative 2 and 2, concaving up in the other places. All right, next problem. Determine the points of inflection and discuss the concavity of the graph. That's basically what we've been doing this entire time. So we're going to do it again. This one looks like a nice equation to take the derivative of. So first derivative, power rule, 4x cubed minus 12x squared. Second derivative, power rule again, 12x squared minus 24x. So just like before, we set this to undefined, set this to 0 to find our possible points of inflection. This is never undefined, so we just set it equal to 0. And then we'll factor. So we'll go 12x, x minus 2, x equals 0, and 2. So those are the possible points of inflection. Now let's remember what a point of inflection is. A point of inflection is where it changes concavity, from concaving up to concaving down, or vice versa. So if we get something like concaving up here, it's just not a point of inflection. It's like we said, these are possible points of inflection. So let's look at it. So let's plug in, where's our second derivative? Our second derivative is right here. That's probably the easiest form to use. So if we plug in 1, we get a positive 12 times negative 1. So it's concaving down here. So I'll put a negative sign. If we plug in 3, we get a positive times a positive. It's concaving up there. If we plug in a negative 1, we get a negative times a negative. That's a positive. It's concaving up there. So actually, this graph just looks like concaving up, concaving down, concaving up. So our points of inflection are at x equals 0 and at x equals 2, because that's where it changes concavity. Now, they did ask for the points. So let's go and find the y values. And so again, think about what we want. We want the y value of the function. So do we plug into the original, the first derivative, or the second derivative? We plug into the original because we just want the y value. So when we plug in 0 to the original, 0 to the fourth minus 0 cubed, we just get 0. When we plug in 2, we get 2 to the fourth, 16, minus 4 times 2 to the cubed, minus 2 to the fifth, minus 32. So that's 2 comma negative 16. That's where it changes concavity. So let's take a gander at the graph then, just because we've had fun with that. So what's our original graph? X to the fourth minus 4x cubed. And let's see, is what we said true? So it definitely doesn't look exactly like what we said. But that's still going to be true, because you see here at 0 comma 0, you kind of can tell that gets the vibe from like going up and to going down. And then at 2 comma negative 16, you can see that's also where it's kind of switching from going down to going up. So points of inflection, you can't really just look at the graph and tell, but when you see them, you can kind of be like, yeah, you can tell that it turns around there. And yeah, discuss the concavity. We didn't write it, but it's concaving down from 0 to 2 and concaving up everywhere else. Let's see. It looks like I just did a repeat problem there. And this is the last problem. Find the relative extrema for that. Okay, so I see what they're getting into here. So the idea here is what's called the second derivative test. So last time in the last section, to answer this problem, we used the first derivative test, which is what we've been doing, where we find the possible points and look at what's in between them. But that's not what we're going to do here to find the relative extrema. What we're going to do here is we're going to think that, so we're going to find the possible values, and then we're going to say, well, if it's a maximum, what does that look like? That looks like this, right? And that's our maximum point. So notice that if it's a maximum, it's concaving down there. And so the second derivative is negative, is less than 0. And if it's a minimum, it looks like this. It's concaving up. So the second derivative is greater than 0. So notice how that's a little counterintuitive. For the minimum, you want a positive second derivative. And for the maximum, you want a negative second derivative. But you can see why that's true. So now we're just going to do that. We're going to find our critical points, just like we did yesterday. So we're going to find the first derivative, which is just a power rule. And we're going to set that equal to 0. So we get x squared times negative, I'm factoring out a negative 15 as well. I'm factoring out a negative 15x squared. So I get x squared minus 1 here. So I'm getting x equals 0 and plus or minus 1. That's where we have to look. That's where we have to look. And we're not going to do the number line. We're going to take the second derivative. So this was the first derivative. Now we're going to take the second derivative, because that's going to tell us our concavity at those points. So what's the second derivative? Negative 60 x cubed plus 30x. And so we want to say, is that positive or negative? So when we find f double prime of 0, when we plug in 0 to that equation, we get 0. We get that the concavity is 0. Okay? When we plug in 1 to that equation, positive 1 into that equation, we get, so let's see, I'll write it out. So f double prime of 1, we get negative 60 plus 30, which is negative 30. So there it's concaving down. And at negative 1, we get, in the second derivative, positive 60, but then minus 30, which is a positive 30, which makes sense because it's an odd function. So there we go. Now what did that show us? That showed us at x equals 1, it's concaving down, which means that x equals 1 is a max. At x equals negative 1, it was concaving up. So that means at x equals negative 1, it's a minimum. And at x equals 0, it was neither. So what that means is that it's doing something where it's flattening out and then going back. So the concavity does flatten out. Let's see, that's not right though. But basically it's going to flatten out and then not change concavity. I guess it doesn't totally need to flatten out entirely though. But let's take a gander at that. Basically it's not going to be a max or a min at x equals 0 because the concavity is not positive or negative. So let's look at it. We got negative 3x to the 5th plus 5x cubed. So here's our graph, and you see the little flatten out there. So what were we looking for? We were looking for relative extrema. So we said we had one here at, well, yeah, we didn't find the y value, but at negative 1 we had a minimum. That's what we said. And at positive 1 we had a maximum. And then this, though we said it did flatten out, but it wasn't a max or a min because it flattened out, but then continued to keep going up. And we saw that because the concavity was 0 there, not positive or negative. So that was a good section. So that's the second derivative test. So honestly, most of the time, that is an easier way to find if something is a max or a min. Like somebody in the comments yesterday when we were doing these asked why I didn't use it because they saw it would be so much easier. And I said, well, because we haven't learned it yet. We learned it tomorrow. But now that we've learned it, that's definitely the easier way to do things.